Okay, thank you very much. So today I would like to present my work. The title is Acoustic Feature Aggregation for Acoustic-Linguistic Information Fusion. I'm from Acoustic. So my main theme for my PhD research is the study of speech emotion recognition with acoustic and text feature or lexical feature, and the two themes is divided into two. The first is acoustic feature aggregation, and the second one is acoustic linguistic feature fusion. So before starting my motivation and background, I would like to explain brief about the block diagram of dimensional speech emotion recognition. So the first is we need a data set, and then there is two main blocks. The first is feature extraction. The second one is classification or the model. So professionally, I working in classification, and now I'm working with feature extraction. We can also use some pre-processing methods, like some previous presentation using silence remover or others, and then the output is three emotion attributes: valence, arousal, and dominance. So this the main block diagram of dimensional speech emotion recognition. So the main block on the two feature extraction and classification. So for today's, uh, I would like to combine acoustic and linguistic information. The motivation is the first is human processes information in multimodal way. For example, in McGurk effect, the difference between visual and uh, sound will affect the different result. For example, if the the sound is ga, but the visual the lips is uh, da, so we use ga. We listen ba instead of ga. In my opinion, in sound and I mean in acoustic and textual is also the same. If the meaning or the semantic is different with the acoustic sound, so the meaning will be different. In case of speech-based application, because the target application is speech-based, like telephone call, voice message, and voice-based application, two feature can be extracted. The first is acoustic feature, and then the second one is a linguistic feature or lexical feature or semantic feature. And move to emotion. Emotion is one of the challenging human perception, which can be extracted from speech, and using the previous two feature, acoustic and linguistic, because both feature can be extracted from speech, we can estimate the emotion from speech. In this case, the goal is to predict the valence of an arousal. Valence is the degree of the from pleasant to unpleasant, from negative to positive, and arousal is the degree of activation from sleepy to very active. And this research aimed to predict valence and arousal categories, not the continuous degree, by using acoustic feature and linguistic feature by acoustic feature application. I will explain it later. So the data set is from Interspeech Compare Challenge 2020 this year. So I submit the paper for the Interspeech Challenge. There is three challenges in the computational paralinguistic. One of the challenge is to detect emotion, in this case, valence arousal from the elderly pupil. The name of the dataset is Alm State of Mind in Speech Elderly Corpus. The language is German or Dutch. Besides providing the dataset, the organizer also provide the baseline feature, but not combination. The first is acoustic feature. There is four groups of acoustic feature, and then one group of linguistic feature. And they provide labels in valence and arousal. The original labels is in numerical value from 0 to 10. So the variant is 0 from 0 to 10, and the arousal from 0 to 10. But the organizer converted this numerical value from numeric to categories. So there is three categories: low, medium, and high. Low is from 0 to 6, medium is from 7 and 8, and finally high is 9 to 10. So only three categories from for valence and arousal. And this is the data set. It's very small data set. And they divide into three: train, development, and test. And they give all this partition. Usually the test partition is kept by the organizer, but in this challenge, they provide all data set. And they divide into two types of data. So, for example, for storage or for text text information or text feature or transcription, they give in stories. They call it stories or utterance, maybe utterance close to stories. And for audio, they give it in chunks. So one chunks consists of, for example, 40. One stories consists of 40 chunks. So a chunk is part of stories. One stories consists of many chunks. So the audio is given in chunks, and the text transcription is given in stories. So it's different level processing. And the number of stories is 261 for stories, and the chunk is 7,000 chunks. One chunk is about 5 seconds. And although the dataset is balanced between train, development, and test, but it from each category, for example, low, medium, and high, is imbalanced. So different. Maybe the most is in low because the score is from 0 to 6. And the problem is by nature of the dataset, given audio file per chunk, text and labels per story. So how to aggregate acoustic feature. So it means that how to obtain acoustic feature per story, not per chunk based, because the audio file, well, file is given per chunks, and label is given per story. And that's the first one. And the second problem is how to combine acoustic and linguistic feature, because I said previously, the size or the level is different. Acoustic feature is extracted per chunks, and a linguistic feature is extracted per stories or per utterance. So for one story here, it's the contents it consists from many chunks, and but the labels and is given per story. So one story, only one label: low valence, high arousal, and others. But the acoustic feature and audio file is given per chunk. And maybe the future or the original aims is what's the best method to represent the emotion within a story. To solve or to answer this research problem, so we propose two methods. The first is feature aggregation, by aggregating acoustic feature from chunk to stories. And then the second one is by feature concatenation, by concatenating acoustic and linguistic feature. So to achieve the second solution, the first must be performed because uh, the size of the feature is different. So we want to make it the same, for example, one dimensional vector to concatenate those two kind of feature. So the purpose of uh, my main theme, not the origin today, is to propose methods to fuse acoustic linguistic information for specifically dimensional speech emotion recognition. And for today's is to evaluate the effectiveness of early fusion acoustic linguistic information fusion compared to the baseline model and baseline results. And as sub goal or sub purpose, I want also to compare the result in unimodal in acoustic only result by using feature aggregation compared to the original majority voting. So the original or the baseline method used majority voting. It means they compare the result after the classification and then use the most uh, labels to represent one story. Sorry. And for the baseline features, they provide five. Yes, the first is acoustic. For acoustic feature, first is compare from the challenge itself. It consists of 6,373 static feature, and then Open Expo using text of audio words using different codebook, and they use deltas also. Actually, they use 100 codebook until 2000 codebooks. So the result is from 2000 to 200, I think, until 4000. And they also use feature from deep learning using deep spectrum. And the size is 2000 dimensional, and finally they use AU deep using 1000 dimensional feature. And for the linguistic feature, they use, I think this one, the newest one, word factor from PRT from Google, I think, but they use different configuration. For example, using global maximum pooling and PLSTM with attention and PLSTM attention and part of speech, and the fuse of those three feature. So they also provide this acoustic feature. And from my proposal, I add one more feature based on the Librosa feature extractor and my other research and my professor research. So I compound acoustic feature using MFCC, 40 MFCCs, 12 chromas, and then filter bank with 1128, and then spectral contrast, centroid MFCCs, and delta MFCCs. The total is 273 for one frame. So the size, number of frame, and this number. And because this feature is very big and the previous uh, provided feature is only one factor, so I extract mean and standard deviation from this feature. So mean and one standard deviation. So the total is 546 dimensional feature for one chunk, not one story. And this is the visualization of the previous feature explanation. So for one utterance, divided into many frames, and for one frame, we extract 273 features. So for one utterance or one story, there is uh, n frames multiplied by 2000, 273 feature. And for aggregating, so the aggregation is done by mean and standard deviation. So we calculate mean of MFCC chroma and filter bank, and also I calculate the standard deviation of this feature. So for one utterance or one story, we obtain one vector with 546 dimensional feature. So now the size is similar to the linguistic feature. And for acoustic only emotion recognition, so this is the block diagram. So for each chunk, this is the baseline provided by the organizer. For each chunk, they input the acoustic feature to the SVM classifier, and then they obtain the predicted valence and arousal degrees categories. And so for each story, there are a lot of many results, and to obtain result for one story, they use majority voting. So they use the most used label as the final prediction. So here they use output aggregation, not input aggregation. But I propose to use input aggregation or acoustic feature aggregation. And because the data is very small, only 261 stories or utterance, I do data augmentation. It means I add or decrease the data. In this case, I do upsampling by adding or copying more samples for under-resourced class. For example, here in low arousal, there are only 31 uh, data or 31 stories, but in medium categories, there is 94 data, and in high categories, there are also 49 stories. So the factor is computed by this calculation. The maximum is 94, and then modulo divided by the lowest one, 33. So the factor is 3. So I multiplied this data to by 3. It's not the same, but the similar. The number now is better than the previous one. So that's what I mean by data augmentation, by upsampling the under-resourced class to close to the other data in other classes. And for acoustic feature aggregation, I propose the following methods. First, for one story, it's divided into some chunks, and for each chunk, uh, we calculate the acoustic feature, and then uh, we aggregate acoustic feature for each chunk. For example, using two methods. The first is by using mean value. The second is by using aggregation. So for mean, we take the average score from for one story, all chunk in one story, and for maximum aggregation, we take the maximum acoustic feature, maximum values of acoustic feature in one story from all chunks. Then uh, uh, then we got acoustic feature for one story, and then we processed using SVM, the same classifier used by the baseline, and then we got the label for one story and also for other stories. So here we obtained the label for each story. The difference between the baseline processed chunk directly, and then the result is in chunk based, not in story based. So, but here the result is in story based or in utterance based. And as I said, I used two methods. This is not the feature extraction, but the aggregation method. For feature extraction, I use mean and standard deviation, but for aggregation, I use mean and maximum value. So for mean, I calculate the maximum value. For example, the number of feature is uh, all frame is, for example, 100 frames. So I calculate for each MFCC, each chroma, each filter bank, I calculate the mean value of those values. And for maximum aggregation, I only took the highest maximum for all chunks in one story. And the benefit of this method is by using these aggregation methods, it will enable me to concatenate the acoustic feature with linguistic feature, because that's my next goal. And for acoustic linguistic information fusion, there is some methods can be divided into two main methods. The first is the early fusion, or the feature level concatenation, or feature level fusion, and then the second one is late fusion, or decision level fusion. So others two I already did it in the past. So in the current work, I do feature concatenation, because I think it is the simplest one, because only use one model. If you use network concatenation, we use two model and then we concatenate. And in late fusion, it needs more steps, because each feature processed independently, and then the result is combined. Yeah, so this two process, while feature concatenation is only one way processing, because we only process both feature in the first, and then we compare it and then input on the same network and then obtain the result. So this is the visualization of feature concatenation. For example, for acoustic feature, although the number is different here, for example, acoustic feature is 456 and linguistic feature is 512. Okay. So we can concatenate here by using feature concatenation, and after we got the whole feature, we can input to the SVM and then obtain the result. So this is the result for the baseline. So I obtained directly from the paper, a patient paper. So there is three challenges here: elderly emotion challenge, and then B, I think breathing, and then mask using masker, like now what we did to detect sound with and without mask. But I only focus in this elderly emotion challenge. So and they use five feature, four from acoustic and one from linguistic. So here the result from development: A is arousal, V is valence. And the highest, for example, in development is uh, valence is Gmax here for valence detection, and for arousal is open expo using 125 codebook is 42. And for test, the highest score is using PLITT, a linguistic feature here, and the arousal, the highest one is ResNet here. So the challenge is the goal of the challenge is to improve the score using the given data set. So we can see here also if the one of the disadvantage of this method and the data set, I think that the best score in development, for example, here the development Gmax is not the best in the test sets. So that's the problem here. And move to my results. So I propose to approach. The first is by acoustic feature aggregation, and the second is by linguistic acoustic linguistic combination. For acoustic feature aggregation, I used additional feature like prosa here, and then this is the reference from the previous tabel, and I used two aggregation method: mean aggregation and maximum aggregation. And using mean aggregation, I think the highest the one for valence is using maximum aggregation, using compare result here, and for arousal, the highest one is by using mean aggregation using open expo with 125, yeah, 125 code books. So we can see here that the mean aggregation and max aggregation obtain the better result compared to the baseline. Actually, my future goal is to uh, combine acoustic and linguistic, but I observed that using acoustic only, uh, acoustic aggregation, the result is better than using majority voting as provided by the baseline paper. And the next result is by utilizing acoustic and linguistic information fusion. So this is the result from the all combination. So for example, the acoustic feature of the Libros and linguistic is the four linguistic feature from the baseline, and we observe that the the best result for development is by using our proposed Librosa and Gmax for linguistic, and for arousal is using AU tip and Gmax, I think here. Because the for test set the data is very limited, only five trials, I think. Yeah, yeah, they log only until five submission the 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 submission. So I only submit the result, some of, not all result, but some five result only. And this the result that I submitted to the organizer. The first, this the baseline, the highest, for example, the highest one for acoustic, for example, using ResNet, and the highest for linguistic using PLIDT. So I proposed four here because I think one is filled, and we can see here that the combination of acoustic and linguistic feature improve the baseline unimodal, because the baseline only provide unimodal acoustic and or linguistic result. So you can see here that the average recall score is improved, I think, in all combination. However, for the test set, we only improve the score for valence prediction by utilizing ResNet and PLITT. So both features are provided by the organizer, but we combine it by our methods. So here the ResNet is obtained by aggregation and acoustic feature aggregation here, and the linguistic feature is as provided by the organizer. So some discussions for this research and this challenge. First, the data set is very small, only 261. So in my previous result, I used DNN based, but it cannot be applied here because the data is very small. I already tried to apply it, but the result is worse. And the second, the use of data augmentation by adding more samples for under resource data didn't improve the performance. That is, the score with and without augmentation is the same. And for the proposed methods, there is two proposed methods. The first is acoustic feature aggregation using min and maximum aggregation, and both improve the recall score from the baseline. And comparing these two, the score of min aggregation is higher than the maximum aggregation. And we also proposed one feature set based on LibreSA feature extractor, and this feature compared by the linguistic obtained the highest score for valence, but only in development because we didn't submit it to the test test partition. And the combination of acoustic and linguistic information improves both valence arousal in development, but in test only improve valence only. Thing and I can conclude, or I can summarize, that two methods are proposed to improve the valence arousal prediction: acoustic feature aggregation and acoustic linguistic fusion. And both methods improve the baseline in particular ways, not in all, but in, for example, in development only. And for the best result in this challenge is obtained by combining ResNet 50 by using feature aggregation and PLITT for linguistic feature. And for arousal, the highest one is by using ResNet 50 and Gmax. And there is mismatch between training and test sets given in dataset, and also it's also shown in the result in the baseline paper. I think that's all. Thank you very much. Is there questions? Okay, some question. Okay, the first question is from Una question. Aggregation, it means how to obtain the acoustic feature from chunk to story, because as I said here, the feature extraction, the baseline provide acoustic feature per chunks per, so it's short audio file, but the labels is per utterance per story. So the baseline use the majority voting here. So they process feature per chunk, not per other, not per story, and then the result, and they, for one, for example, one story is 40 chunks, and the result also 40. So they use majority voting to perform which label represent the story. So they use, in this case, they use output aggregation to aggregate between output between chunks to story. And my proposed method, I reverse. So I do aggregation in input. So before I input to classifier, I aggregate the feature. So the feature represent for one story, not one chunk. So I think that's the meaning of the aggregation. So how to obtain feature for one story given chunk file. And for Candy, first it have you check the acoustic feature.
Excuse me, I'm still confusing.
Yes.
Is it a general terminology for using this action? That is aggregate or aggregation?
Yes. Yeah, I think it's in computation,
General term used
in information.
to study this one, but in theory, this word is not obvious to me. So I cannot imagine that what what you so
Yeah.
so human story is speaking so speaking I don't have
Okay. Thank you very much. So I mean, yeah, the word maybe I want. Yeah, I will try to find another term maybe. Acoustic feature for and from for Candy Sang, have you checked the acoustic feature for comparable? Yes. Yes, the acoustic feature for compare is, yes, there's 6,000 feature, and that's the functional or static feature from the dynamic feature. So that's why the for one utterance they only have the compare feature factor is only one factor, the 6,000 dimensional factor. What's the so based on my previous research that I found that also in other paper, it's reported that using mean and standard deviation lead to the better performance. So, and in others, my other paper, I use my previous expense feature, for example, here. So here, it's reported that this feature is useful for anomalous sound detection. So I tried to modify this actually until tonal. So I tried to modify this and add the more feature. The goal is to obtain the similar number with linguistic feature, because the linguistic feature is about 500 and there is no weighting calculation. So the importance of the or the influence of acoustic or linguistic only determined by the number of feature, I think. So that's the first question. Why I propose this imprecise feature? Mm-hmm. Yes. Yes, it is like MFCC is the similar, like a lot of acoustic feature. But as long as I remember, it's just like MFCC, delta MFCC, and also others like Mel spectrogram also. But this number only functional number, static number. So this only statistical, not frame-based processing. That's why only one vector. So this is a functional or static feature from the MFCC and other acoustic feature. So that's the
But I mean that in your case,
yes,
in your case, you also use the link calculation,
yeah,
so it also counts as
yes, as statistic feature.
so
Yeah, actually my goal is to have, because here the linguistic feature only 500. So if the I use large acoustic feature, this acoustic information will influence more than linguistic feature. So I want to design acoustic feature to have the similar. So the influence between acoustic and linguistic is the same, because I don't use any weighting factor in my classification.
I think maybe you can consider the feature recognition feature.
Ah, okay, based on this feature. Ah, I see.
Instead of using some feature.
But feature selection works, for example, here. Okay, okay, yeah, maybe the highest 500 feature. Yeah, yeah, yeah. I understand the highest 500 feature. Okay, and then your second question: how is the condition of the framing that you use? For example, yeah, the framing I use the default, the standard using 25 millisecond of frames for windowing, and for hoop size I use 500 samples. It means 10 millisecond. So 25 millisecond frame and 10 millisecond hoop size.
So in one chunk, in accurate time,
The frame is number is different, because each each story different number of chunks. So that's why the problem, if we use the frame based processing. So here is, for example, the first story is 40 chunks, and then the second story is 50 chunks. So for each chunks the number is different. So that's why I propose this statistical function. Is that, oh, it's called this framing. Okay, do you have an idea where you choose the feature? Okay, I already answer. And then for linguistic I didn't consider other, because the number they this feature is extracted using deep learning, not based on uh, like uh, word factor, or the usual word factor, but that's based on the deep learning. So this is the output of the deep learning. Like this deep spectrum and out deep is also acoustic feature using deep learning. So I don't use any other uh, linguistic feature. I'm not clear with the aggregation method in page 15. Okay, 15. Okay. So here, for example, for one story, so one story, I means the number of the first chunk, second chunk in one story. So for one story, I do both mean aggregation and maximum aggregation. So this is the feature, for example, in one 500 feature. So where I okay, for example, here the first is the mean value for from all chunks. The first chunk, the number for, then the second MFCC, third MFCC, until the maybe the last mail filter bank. So that's the mean value, and then move to the second chunk, the third chunk, and for the maximum I also do the similar, but here the number is the value is I only take the maximum number of the feature.
Why not standard deviation?
Both
Why would
okay, okay, okay.
minimum and maximum?
I think that's this one two acoustic feature, no, two statistical functions that used in the for aggregation. But I think standard deviation will no, standard deviation will represent the deviation, but this number represent the feature. For example, if we have some feature, we have average feature, and then the maximum. My intuition is if one in one utterance, if there is some chunks, so the emotion between story or between utterance may be the highest one or maybe the average one. So that's why the reason I choose the mean and maximum. But if standard deviation, the number didn't represent the feature value.
So these two SIA, external augmentation, and then you use
Yes.
not using both.
No. One on one. I compared this one in tabel. This one the result is this is result for mean and then this is result for maximum. One. Not combination. And then I'm not good with application in which already answered. The score is in UAR, is unweighted average recall, similar to accuracy but per class, I think. So the accuracy between low, high, and medium. Significance of each feature for the question. I didn't calculate this feature importance. You mean the feature importance, right? Yeah, sorry, I didn't calculate it because it's a static function because so there is a lot of feature. For example, 500 feature here is MFC 40 is chromas maybe 13. So only one. If I calculate, maybe I only calculate. I got the number here, but which part of MFCC, not represent MFCC. Maybe in frame-based processing it will be useful, but in static function, I think that because the number also already small, if we use feature selection, it will be smaller, and maybe it will difficult to learn using small number of feature.
So,
Hmm.
but I think you still can like
Yeah, which one is important?
yeah,
Feature, yes,
yeah, for
yes, 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 yeah, yeah. Yes, of course. Which feature is important? Yeah. Okay. Hosang proposed the method for what's the novelty? Yeah. Okay. I think this paper is the novelty is not so genuine. I mean the original is my original goal is to combine acoustic and linguistic information. But to perform this concatenation, I need to perform feature aggregation because the acoustic and linguistic is processed on different level. So that's why I proposed figure aggregation, and the result is better. But I cannot explain why the result is better than majority voting here. So yes, that the contribution I wrote in the paper is the first is the acoustic feature aggregation, Yes, in machine learning maybe it's popular, but in acoustic maybe for specific tasks maybe, as long as I know, it's not so popular feature aggregation in acoustic feature. And my main goal is the second contribution is the uh, combination of acoustic and linguistic feature. Is this also not so original, but the difference is here I process acoustic and linguistic at different level. So for acoustic, I process on chunk based, but for linguistic is based on the story or utterance. So different level processing. I think that's the contribution of the my proposed method. Does that answer your question? I think the term aggregation. I need to check again the term aggregation.